So we're going to discuss proving correlation, proving causation today. And to kind of get started, I'm going to remind us of some things we went over last time when we talked about section 10.1. We're talking about correlation versus causation. So in that section, we were looking at things, and we noticed, for instance, that the price of pizza in New York also went up lockstep, hand in hand with the price of subway tokens. So does the price of pizza cause the price of subway tokens to go higher, or is that something else? Is that a correlation or a causation? Which one would you say there? Correlation, yeah. I mean, one doesn't cause the other. Now, what about somebody's weight versus the number of hours they spend watching TV? Does watching TV cause you to put on weight? No. No. They're correlated, but they're not a causal relationship. Causal relationship is something you would see here. Smoking causes cancer. It took years for people to establish this, but smoking does cause cancer. Moving down, the number of searches for flu or flu-like symptoms on Google. Does that cause the flu? No, but there's a correlation. In fact, for a while, they were tracking flu trends based on Google searches. So for a while, it was pretty accurate, although they did run into some problems, and I don't think Google does it anymore. Owning a dog, there's a paper recently that says owning a dog is correlated with people living longer. Does that mean you should go out and necessarily buy a dog? Should Ahmad trade in his cat for a dog? I mean, personally, I'd say yes, but I'm a dog lover. I'm a little biased. But no, I mean, you shouldn't make drastic changes based on one study. And even the study themselves said that there was an association, which is kind of a fancy way of saying that there's a correlation, but they haven't necessarily established a causal mechanism, that one causes the other. So there's a few steps that you should go through to establish causation. And that's what we're going to work on today, is how can you establish that one thing causes another. Now we're going to do that with global warming as our example. Now, you do not have to agree with me on this in terms of whether or not man-made carbon dioxide is helping create global warming, but you do have to understand certain things about proving causation, and I'll use global warming as my kind of example case. So with that, let me list for you some things to know. There's going to be 5 things that are going to be on my list of ways to help establish a causal relationship. So you should know all those 5. I'll list them for you in a little bit.
What section is this?
It's not a section. So this is not in the book. So hopefully you're taking good notes, but I'm telling you exactly the things you need to know. You need to know what a longitudinal study is. Now I'm discussing a longitudinal study. We'll talk about something called a confounding variable. So we'll figure out what the confounding variable is. And I want you to know the difference between climate and weather. So these are the things you should pick up on as we go through this discussion. And this is what I'll test you on. I'm not going to test you any chemistry about ice cores or isotopic abundance or anything like that. These are the things that you're responsible for. And I'll kind of try and keep them related to statistics. So, first thing you should see if you're trying to establish a cause and effect relationship is the correct temporal sequence. The cause comes before the effect. So one thing to look out for is this, the correct temporal relationship. Other things to look for is replication of studies. You should see lots of research saying the same thing again and again and again. It shouldn't just be one study says, hey, dog owners live longer. Well, I'd like to think that, but until I see some more evidence, until they can establish it a little bit more, well, take it with a grain of salt. Don't go out and make some big drastic changes. Dose response. So this is something you should see. If there's a relationship between 2 variables, but oftentimes you'll see more of the dose gives you more of the response. And we'll talk more about that in a little bit. You want to rule out confounding variables, other explanations. One way to do that is with a longitudinal study. So we'll have to figure out what a longitudinal study is. And here you have an example of something called a double-blind study. I'll talk about that a little bit as well. And finally, you should have a plausible causal mechanism. You should be able to explain the results you're seeing. Why does one cause the other? Not just that we think it does, but here's how it does. So you should be able to explain that. Now, generally when I get ready for this talk, I don't think of proving causation as a topic that's in the news, or global warming as a topic that's changing rapidly. But there's actually a couple things that happened over the weekend that I brought into our slide presentation. And the first one of them is this. President Trump tweeted out, "Brutal and extended cold blasts shatter all records. Whatever happened to global warming?" What he's doing is he's confusing two things. The two things are things that I want you to know. Climate versus weather. Weather is what's happening outside our window right now. So we got a little light snow that turns into rain when it hits the ground. That's the weather. Climate is long-term averages. What's the weather like in general, on average, throughout a region over a long period of time? So I've heard it reduced to a nice kind of one-liner like this. Climate or weather changes with the day. Climate changes with the latitude, right? If you go farther south, you're going to get more warmer and temperate latitudes. You go farther north, it's going to be colder, etc. But climate is not something that changes just because you get a really hot day or a really, really cold day. Weather is what's changing that fast, not climate. So the idea of there is or is not global warming is not going to be impacted by what happens with the weather. So with that, let's start taking a look at the different 5 things that help us establish a cause and effect relationship. And the first one is the correct temporal relationship. Now, it took decades of effort by lots of researchers to establish that cigarette smoking causes lung cancer. Usually takes about 15 to 20 years for lung cancer to develop. So you can see that in the lag between the increase in the rates of smoking and then 15, 20 years later, the increase in the rates of lung cancer. And then eventually, when smoking peaked and started to decline, eventually so did lung cancer as well. So that's what you'd like to see in terms of a cause and effect relationship and having the right temporal sequence, right? Here's the cause, here's the effect. With carbon dioxide and global warming, it's not quite as easy to see as it is here. So one of the challenges that you run into is that we have a limited amount of data. We only have direct temperature measurements going back to like the 1880s. And before that, not so much. So how do you get temperature measurements before then? You can look at ice cores. So Greenland and Antarctic ice cores. The chemistry is really well understood. You can figure out the temperature which the snow was laid down when the ice core was being formed, and get a good idea of not only temperature but carbon dioxide levels. You can look at fossilized corals. You can look at lake sediments. So there's a lot of different ways you get these so-called proxies for temperature. Growth rings in tree trunks, frozen pollen, marine sediments. So with this, we can kind of establish a picture of what the Earth's climate has been like for much of our recent history, going back to almost 800,000 years ago. But what we see is not the nice graph that we saw when we looked at smoking and lung cancer. So in this graph, the red line represents average temperatures as reflected in Antarctic ice cores. And these yellow dots represent the levels of carbon dioxide. Now, what you'd like to see is the lag between the dose and the response, but we don't exactly see that with ice cores. By the way, quick aside here. Notice that these data points have little wings on them. Can anyone imagine what those little wings represent? Oh, well done. Spot on. Yeah, that's the confidence interval. So each of these are surrounded by a confidence interval, which gives you, a nice measure of where it could be at. But back to the story here. Sometimes it looks like carbon dioxide is leading the way. Sometimes it looks like it's behind the temperature increase. So which is it? Which one's the cause? Which one's the effect? And critics of the relationship between CO2 and global warming point this out. But what's happening is a little bit more nuanced. Changes in the Earth's orbit create a little bit of a warming, and then there's a kind of a feedback between carbon dioxide and temperature. The more warming releases some carbon dioxide from the ocean. Now think of a can of pop, for instance. If you had a can of pop and you pop the lid, what's going to happen? It's going to bubble, right? Now, if it's really cold, it's not going to bubble as much as it will when it's really warm. So the warmer pop is going to release more CO2. And the ocean functions the same way. When it gets warmer, it releases some more of that CO2. Now, when that happens, the CO2 gets up in the atmosphere where it acts as kind of a blanket and helps warm the Earth. So you get this continuous feedback. And the reason that this is not as clear of a temporal relationship is because these things are mixing in and out. But in general, carbon dioxide levels do lead the charge. It's just not always, not initially anyways. So it's not as nice and crisp of a clear temporal relationship as we might like. But it is there, and we do understand it pretty well. Replication of studies. Certainly if there is some kind of a cause and effect relationship, you should see that throughout a lot of different studies. You shouldn't get different studies saying different things. One area that's been tough to nail down is, does cell phone radiation cause brain cancer? Or does being near electrical lines, in terms of where you live, does that cause cancer as well? And it's tough to pin those down. I mean, you get studies that say they do, studies that say they don't. So what level of agreement is there with respect to man-made global warming? Well, the first thing I saw when I looked for something was this petition that was signed online. And, at first glance, it might seem pretty impressive that 31,487 of these people signed this petition that makes a strong statement that says, basically global warming is not real. And when you look at it, it's really not all that convincing. First of all, these are Americans with university degrees in science. But what science? Climatology? Doesn't say. And, if you're studying paleontology, I don't know if that necessarily gives you, as much credence or much weight when you're talking about global warming. So, okay. And only a few of these people say that they have PhDs, relatively speaking. But you know what? You can get people to say pretty much about anything. There's a website online that amuses me. People that still think that the Earth is flat. Wow. It's really a thing. I pulled this out off over the weekend. Flat Earth Society. Yeah. People still think that the Earth is flat. Okay. All right. That's your choice. Now, a little bit more sophisticated approach to trying to tackle this was in this paper by Richard Toll. The problem with his approach, and he basically says, well, there's really not that much of a consensus, and that's because of the way he did his research, and also the fact that if in reviewing a paper in their abstract, if they didn't explicitly say that global warming was the cause of, or man-made carbon dioxide was the cause of global warming, that was a non-position, a non-endorsement of man-made or anthropogenic global warming. So it really puts your thumb on the scale when you do that. So a good question for you is, well, what percentage of scientists should agree before you feel comfortable saying, okay, yeah, there's general agreement here? Now, for comparison's sake, 91% of people believe that smoking causes lung cancer. And the funny thing is that there's actually been a dip down, right? Back in 1999, 2000, 92%. How are we losing ground in that battle? I don't know. Whatever. So the question to you is, what percentage of experts would have to agree on something before you'd say, okay, yeah, there's a consensus? What's the percentage that you would feel comfortable with? I'm looking for audience participation now. 60? More than half? Okay. Anyone else? Jake? 70 to 80%? All right. So the study that I looked at that I thought was most well done and convinced me the most found that 97% of studies done by climatologists agree that we're causing global warming. 97%. Wow. I think that meets your standards, right? The unfortunate thing is that if you ask the public, what percentage, or is there consensus on global warming? If you ask the public that, no, the general public thinks that, 55% of the general public think that there's actually a consensus on global warming. So there's a big gap, right? I mean, I don't know what you all think about a consensus, but to me, 97 sounds a pretty convincing number. Yet, a little bit more than half of Americans think that there's really a consensus on global warming. So I'm not sure where that gap is coming from, and it goes beyond my talk here to try and speculate on that. But 97%, that's a pretty convincing statistic. I think part of the gap might come from problems like this. People have a social media account, and boy, all of a sudden their opinion carries a lot of weight that maybe it shouldn't carry. Don't know. That's just a guess. Okay. So what else should you see in terms of establishing a cause and effect relationship? Dose response. More of the dose gives you more of the response. So do we see that? Now, personally, I think of this, when I see this, I look at it and I think of people consuming alcohol. At first the effect is giddy, and then sleepy, and then more and more serious problems. So is there a dose response between carbon dioxide and temperature? Well, let's look back. As I mentioned earlier, we have data on CO2 and temperature going back 800,000 years. So that's a long record. Now I'll let you tell me. Look at the red graph and look at the blue graph. The blue graph is CO2 levels, the red graph is temperature levels. Do these seem to go up and down more or less together? Seems like they're pretty well correlated, right? One goes up, the other one goes up, one goes down, the other goes down. So it seems like there's a pretty strong correlation there. Does anyone see a problem with this graph? A concern with this graph? Yeah, right there. The last 200 and some years since the Industrial Revolution, we're sending CO2 levels off the charts, at least historically. So, and that's old CO2 levels. So, what are they today? Well, 406. And it's actually a little up and down. It depends on the time of year. Okay, so we're at a lower point during the year. The high points occur in May. So there's one last June, and here's where we're at as of more or less today. So they measure these things at the top of a volcano in Hawaii to try and get something that's about as unbiased and well mixed as possible. So, all right, so let's talk about another means by which we can establish cause and effect relationship, and also talk about something else, which is confounding variables. Now, I think I have these slides in a different order than I might like them, but we're going to have to go with it. And we're going to talk about confounding variables first. So a confounding variable is something that's going to kind of muddy the waters between a potential cause and effect relationship. So eventually we'd like to be able to try and figure out, well, is there something that causes something else, or maybe there's a third variable in between them that has this kind of relationship. So what is a confounding variable? Confounding variable is something that kind of comes, it doesn't come between a cause and effect, but it's related to both a cause and effect. So here's three things that must be present to be a confounding variable. Confounding variable is a variable whose presence changes the relationship between the independent and dependent variables, between the cause and between the effect. So it's related to both, and it changes that relationship. Confounding factor must be associated with both the risk factor of interest and the outcome. So it has to be associated with the cause and effect. The confounding factor must be distributed unequally amongst groups being compared. So this last part really is kind of hinting at the power of what we're going to look at next, which is the longitudinal studies. In a lot of these studies, what we'd like to see happen is you have two groups under study, and those groups are pretty much equal, except one gets maybe the treatment medicine and the other one doesn't. Other than that, they're pretty much the same, and then you follow them to see who gets sick and who doesn't. And then any difference in the outcome that you see can be attributed to the one difference in those two groups. Now, hopefully, you have those two factors or other confounding factors are equally distributed amongst your two groups so that there's really only one difference. And then any difference in the outcome can be attributed to the difference at the start. I'll put this online as well, my PowerPoint, in case you're trying to rush through and copy all this stuff down so you don't have to worry about that part. You don't want your confounding variable to be on this causal pathway. It has to be apart from this. So you don't want it on the pathway there. But let's take a look at a potential confounding variable. Did you know this? Ice cream sales cause murder. That's true. If you plot ice cream sales throughout the year, and you plot the murder rate, you get this graph. So, wow. That looks pretty bad, right? I mean, look, February, low ice cream sales, and then it starts increasing, and so does the murder rate. Question?
Well, I was just going to say that the murder rate goes up in the summer.
It does, and so does, yeah.
That's obvious with the ice cream part.
All right. Well, I'll tell you what. So, yeah, the murder rate and the ice cream rate peak at the same time. So, if there is a causal relationship, then one possibility is that murders cause people to buy ice cream. Well, that doesn't make sense. No. So maybe it's the other way around, right? Ice cream causes people to murder, right? Somebody got the last quart of Ben & Jerry's ahead of you, and you're pretty pissed off. All right. Maybe that's not the case then. So what could be the case? And I think you were kind of alluding to this. That there's a confounding variable, which is the weather, right? If it's cold outside, there's fewer people interacting with each other. Maybe tempers don't get flared up as much. And at the same time, when it's cold outside, people are less likely to buy ice cream. On the other hand, when it's hot outside, there's more social interaction. And of course, when it's hot outside, a great way to cool off is with some ice cream. So it's not really that ice cream causes murder. It's the weather. So the weather is a confounding variable. It changes the relationship in both purchase of ice cream and the murder rates. So that's a good example of a confounding variable. We're going to apply that to cross-sectional and longitudinal studies. So a cross-sectional study is kind of what the name suggests, and that is you're going to look at a cross-section of society or some segment of it, and you draw some participants, get some data from them at just a one shot in time, and that's it. You're going to collect data from them, and you can use that to establish some associations, that owning a dog is associated with living longer or things like that. But what you can't do with that is use it to establish causation. And here's where longitudinal studies are great. Longitudinal studies, you pick a group, or better yet, two groups of people, and follow them throughout time and observe them. So the challenge with longitudinal studies, sometimes called cohort studies, is that they're costly. It costs a lot of money to, first of all, identify a group of people, get them in your study, and then follow them throughout time. It's difficult. And it takes a lot of time. Usually you follow these people for years, in some cases decades. A lot of what we know about heart disease comes from a famous study called the Framingham Heart Study. And they studied these people for decades. In fact, they're on their third generation of studying these people. So their kids and their kids' kids, basically their grandkids, are enrolled in the study. So enormously expensive, but very beneficial. And there's loss to follow-up. You lose track of people become disinterested in participating in the study. So there's a lot of challenges with a longitudinal study, but it has certain advantages. One of them is that they're flexible. As you're going through the study, you might realize, oh, well, maybe we need to measure people's blood pressure, and then you can go back and get people's blood pressure. Or other circumstances change, and you realize, oh, well, we should adapt. Kind of an infamous case of this is with sildenafil citrate, which was originally tested to be a blood pressure medication. Yeah, he already knows this story. Blood pressure medication from Pfizer. And they quickly realized that it wasn't doing what they expected. And they asked the old men that they were studying to, all right, hey, you know, this isn't working. We're going to end the study early. Give us our medicine back. And the guys said, no. And, and they're like, they grew a little curious. And they're like, well, why? And I'll let you kind of figure out why. The punchline to this is that the name that you would recognize sildenafil citrate under is Viagra. So, anyways, so these studies can be adaptive, and that's a good thing. It's a good thing for the study, and it helps you identify and establish a cause and effect relationship. Now, here's where a longitudinal study can really help things out, is if you have groups that are equal, if you can measure all kinds of different variables and see that only one of them is different amongst one group versus the other, then you can really start to rule out confounding variables and say, all right, well, you know, all things being equal, this group lived longer. Why are they different? Oh, they had a healthier diet. So you can try and establish that cause and effect relationship. And that's the great thing about longitudinal studies that you can't do with a cross-sectional study. There's also retrospective studies, which are a little bit more suspect because they're asking you to think, well, 20 years ago, did you eat a healthy diet? Sure. All right. It's a great quote here by Sir Arthur Conan Doyle. How often have I said to you that whenever you've eliminated the impossible, that whatever remains, however improbable, must be the truth. And that's what you're doing with a longitudinal study. If you have groups that are the same, except they're different by one thing, then any difference you see in the outcome probably goes back to that difference in the initial groups. Let's bring this back to global warming. A lot of critics of the idea that the extra carbon dioxide we're putting into the air is causing global warming point to different things. They'll say, oh, well, the amount of sunlight that's emitted from the sun has changed. And that's true. It does change. It changes on an 11-year cycle. You see that from the amount of solar or sunspots that we see. Changes in the Earth's orbit. That could be a confounding variable. Changes in the Earth's orbit change how much sunlight we absorb. Volcanic eruptions can contribute CO2 to the atmosphere. Climate's changed naturally in the past. It's doing so now. Well, I'm going to address a couple of these. I don't have time to address all the different confounding variables, but with respect to the amount of sunlight changing, if the amount of sunlight that we're getting, the amount of energy we receive from the sun, is causing an increase in temperature, then what you would expect is that it would warm the entire atmosphere. It would warm the lower atmosphere as well as the upper atmosphere. If, on the other hand, that it's the amount of carbon dioxide, the extra CO2 we're putting in the air, you would expect warming the lower atmosphere, but not the upper atmosphere. So that's what you would expect, and that's actually what we see, is a decrease in the temperature of the upper atmosphere and an increase in the temperature of the lower atmosphere. So as far as that is a confounding variable, we can eliminate that. The amount of change in the amount of sunlight is not a confounding variable for us. The Milankovic cycles. There's 3 different things that change in the Earth's orbit that change the amount of sunlight that we get. There's the eccentricity. That's how drastic of an oval this is, or in some circumstances closer and closer to a circle. The axial tilt and the precession of equinoxes. So it's the precession of equinoxes, the obliquity and eccentricity. Those are the 3 things. I'm not going to try and get into these things, but basically it swings the amount of sunlight we get. But if that was the case, we should actually be experiencing some global cooling. So, and let me direct you back to here. Does this look like it's part of the natural pattern in any way? Not really. So, again, these changes in CO2 levels are certainly man-made. They started around the Industrial Revolution around 1750 and kind of gone off the chart. All right, plausible causal mechanism. If there is indeed a cause and effect relationship, you should be able to explain this. You should be able to say, all right, well, why is it causing this? And we can explain this. How do we know that the greenhouse effect is real? In terms of CO2 being a greenhouse gas, we've known that since the 1850s. In 1859, this experiment was set up by John Tyndall, and it reflected his desire to figure out, does carbon dioxide absorb infrared light very effectively? And it does. We've known this for a century and a half. We can also make predictions as to how warm a planet should be in the absence of carbon dioxide and how warm it actually is. So when you compare how warm a planet should be with how warm it actually is, what you see is that we're actually a lot warmer on Earth than we would be without carbon dioxide. Carbon dioxide is not a bad thing. We probably wouldn't be here without it because it helped keep us a little bit warmer than we would be otherwise. We just don't want too much of it. Too much of it's going to be a problem. But, you know, carbon dioxide itself is not bad. But there is too much of a good thing. Here's a nice schematic of what's happening. When the sun warms us through solar radiation, some of that light is reflected off the Earth's surface and bounces back into space. With our greenhouse gases, which include not only carbon dioxide, but methane, nitrous oxide, and water vapor, a lot of that gets re-reflected back down to the Earth and trapped in the form of infrared light and heat and energy. So it's like putting a big blanket on the Earth, and it's keeping that warm air and that energy in the lower atmosphere as opposed to letting it radiate out into space. And like I said, it's not just carbon dioxide, although that's the big thing, but it's water vapor. Water vapor kind of amplifies this effect of carbon dioxide. Methane. Where do you see methane produced? Yeah, yeah. Basically, cattle farts, pig farts, produce a lot of methane. And I think methane is even more efficient as being a carbon dioxide or a greenhouse gas than CO2. But it's all a problem. Interestingly enough, we do have kind of a case and control here. So here's a picture of Earth and its average temperature, along with our twin planet. What's our twin planet? Not Pluto. Pluto got demoted, right? It's a planetesimal or a plutoid or whatever fancy word they have for it, but Pluto's not even a planet anymore. Yeah, it got demoted. No, Venus. Venus is roughly our size and our composition. So Venus is a little bit closer to the sun than Earth is. They're about 2 light minutes closer. So we're 93 million miles away on average. Venus, I think, is like 67 million miles away on average. So you'd think it'd be a little bit warmer, right? How much warmer? What do you think the average temperature on Venus is? All right. Well, tell you what. Let me just do the big reveal then. 880 degrees Fahrenheit. Wow. That's hot enough to melt lead. Why is it so hot? It actually gets less surface sunlight than we do, because Venus is covered with clouds. And that cloud layer reflects a lot of light here. That's why Venus is so bright in the nighttime sky. It's very, very bright because most of the light gets reflected and very little of it gets down to the surface. But it's that warm because Venus is covered in a thick layer of carbon dioxide. So it's very effective at trapping its own heat. It's stifling there. We've only put things on the surface there once. I think it was a Russian space probe that managed to send us a few startled squawks for about 20 minutes before permanently shutting down. So, but you can't explain the warmth that Venus has on the surface by the fact that it's much closer to the sun. Picture this. Here's the sun, 67 feet away, you're standing at Venus, and 93 feet away, your friend is standing on Earth. If you're standing 67 feet away from a fire, you're going to feel warmer than your friend at 93 feet away. But do you feel that much warmer? No. So we know carbon dioxide is a greenhouse gas, and it can have a big effect. We just don't want to see it have that kind of effect on Earth. So let's bring this back to some statistics in terms of type 1 and type 2 error. Our null hypothesis is that global warming is not man-made. The alternative hypothesis is that it is man-made. So there's 2 correct decisions. If global warming is not man-made and the data fail to reject that hypothesis, that's a correct decision. If global warming is a man-made problem and we reject H0, that global warming is not man-made, again, that's a correct decision. But there's 2 different errors, right? Type 1 error and type 2 error. Let's examine those and think about the consequences of those. First of all, in words, what would a type 1 error be? What are you saying is happening if you make a type 1 error here? So a type 1 error would be saying that, global warming is a problem when it's really not happening. So, yeah. So what would be some of the consequences of that? If we started doing a lot of things because we thought global warming was real and it wasn't, that would lead to increased energy cost, loss of jobs in the fossil fuel sectors, some inconvenience, price of commodities, simple things would go up, like that bottle of water you're drinking. From my understanding, if you take a bottle, any pop bottle or whatever, it takes about 1/3 of the volume of your bottle in oil to make that, in terms of the energy generated, and actually just, there's oil used in production of that. So about 1/3 full of oil. So it's a good thing to recycle those things, use those filling stations, etc. But there's definitely some negative consequences to acting rashly. Of course, there's also this possibility as well. All right, I kind of find that one amusing. All right. You're supposed to make me look good, remember? Hey. All right, there we go. Thank you. All right, well done. There's a type 2 error. Failing to reject the hypothesis that global warming is not a man-made problem when it really is. So, what are the consequences of not doing anything when it really is a problem? So, severe weather. Again, we've seen that this semester. Where have we seen it? I don't know, maybe Hurricane Michael. 36 people dead, and just communities devastated. How about on the West Coast? What's going on out there? Fires. Last time I checked, it was 87 people that died. 600 people were still unaccounted for. That's staggering. You know that death toll is going to go up. And of course, there was 12,000 people, I think in one city alone. 12,000 people were left homeless. 20,000 businesses and homes together were destroyed. Wow. Warmer weathers mean spread of more diseases. Diseases like the Zika virus. Man, as a dad, I look at that and it tears me up. Think of my kid suffering from some kind of disease like that. Reduce agriculture. So if your areas of the world are going to experience more rain, and some are going to experience more drought. And a lot of those areas are going to be areas that can least afford to handle it. Areas in Africa. Rising sea levels. This is going to be a problem for people who live in the coast. You're going to have areas that are just going to be underwater. In fact, this is only if there's like a 3 to 6 foot rise in sea levels. If the polar ice caps were to melt completely, any idea how much sea levels would rise? 200 feet. There'd be a lot of coastal cities that wouldn't be coastal cities anymore. Change of migratory patterns, extinction of species. Polar bears are taking it on the chin with global warming. They just can't feed enough and hunt enough because there's less and less ice for them to swim on. Health threats, air pollution is going to be worse if we keep on pumping fossil fuels and their byproducts into the air. The oceans are going to become more acidic, and we depend on the oceans for a lot. And this one came out over the weekend. So like I said, it was kind of funny in preparing for this. I don't think of global warming as a fast-moving story, but this one came out over the weekend. The U.S. government released a report talking about how global warming will impact the economy by hundreds of billions of dollars a year. So, wow, this is from the government. It's not from some liberal think tank or anything like that. That's from the government. So, lots of potential problems. Which one sounds worse to you? Type 1 error or type 2 error? I think type 2 sounds pretty bad. I like this one. There's no planet B. There's no plan B. We're stuck here. So hopefully we'll do something to make some changes. The news that came out earlier this semester is that they figure unless we change our trajectory in the next 12 years, that the changes we're going to see are going to be irreversible. So hopefully we'll make some changes. Here's my challenge to you. Write a letter to your grandchildren to be open in 50 years. Dear grandchildren, as I write this in 2018, many people are arguing whether global warming is a real problem, and if so, how serious it will be for you when you're my age. I have examined the evidence and decided to, and then fill in your decision. Hope your world's a good one. Love, Grandma, Grandpa. So, anyways, kind of recap here. Things you should get. 5 different things we went through. Improving causation. We talked about what a longitudinal study was. We spent some time on confounding variables. Know the difference between climate and weather. Now, if you want a little bit more on this subject, there's a town hall meeting. It'll be aired this coming Monday, so a week from today. You can check it out on Facebook, YouTube, or Twitter. Any questions, comments, thoughts? Yes? No? No? All right. Well, there are a few more costs to using fossil fuels, but I stole this slide from somebody, and I can't quite attribute all of these things. But hopefully we'll make some changes. All right. Thank you.